everyone. Please come in and be seated. I was informed that I have to be a little bit more strict with time. So now we have the second session in the morning. It's given by Yueh-Ning Lee from National Normal University, NTNU and the Protoplanetary design.
Okay, thank you. So I'll be very quick and very on time. I try to be. So today I'm going to talk about some very recent results that we obtained. Actually, it's a simple recipe for protoplanetary designs that I'm going to propose to you to use to cross-check with your observation results. And this is really freshly out of the oven, so I haven't been sleeping a lot during the past 2 weeks because I've been too excited about this. So I hope you will find it as interesting as I do. And so here are the collaborators. Bashon is actually a summer student who I worked with during the last summer, and Pierre Marchon is a friend and classmate during my master's degree, and Patrick is my former PhD supervisor. And so I'm going to talk about this stage of disk formation, this stage where the disk is still very embedded within a collapsing envelope. So actually all the disk properties should be highly linked not only to the star itself but also to the inflow envelope. And eventually we can find some sort of self-regulation that leads to a disk size that is the result of the central gravitating protostar and also the inflow envelope that brings in mass, angular momentum, and magnetic flux. And yeah, so here are some compiled observation results of disk radius plotted against luminosity. And well, the major conclusion is there are some dispersions, but the major conclusion is that disks are not very large. So typically there are of the size of a few tens of AU at this class 0 and class 1 stages. And class 1 disks could be a little bit larger, but not significantly. And so I list here a non-exhaustive list of a lot of high resolution studies. You must know better than I do already. So these are the current status of what we know about protoplanetary disk size. And so this is, actually if you consider angular momentum conservation, then we have a serious problem, but we all know that angular momentum is not conserved in this context because they are sent away by the magnetic field lines. But still, we start with a hydro model to show you what a disk would be like if we have no magnetic fields. So basically, we have a size that scales with the mass of the star disk system, and the typical size is a few hundred AU. So you can take this as an upper limit of the disk size that you obtain at the very early stage if none of the angular momentum is removed by magnetic field or other jet wind mechanisms. So this must be smaller than this size, but how small exactly? So here I show you. You must have seen a lot of this kind of beautiful images from simulations, but there is one important point that I want you to keep in mind, which is that if you look inside the disk, then it's a mess. So the field lines are dominated by the toroidal component due to the rotation of the disk. So if you try to measure magnetic fields from an envelope disk system, what I would suggest to look at would be to measure around the disk and to try to quantify how much field lines are threading the disk. So really quantify what enters this region would be more important than looking at what's the strength in this region because it's dominated by the rotation. And this is what we are going to take to model our disk. We are going to look at the magnetic flux at the edge of the disk in order to study how the disk is regulated through the interaction between the envelope and the disk. So I think you all agree that there's no longer magnetic catastrophe, so we're happy now. With the non-ideal MHD, we are allowed to remove part of the in magnetic field so that the angular momentum can be somehow, well, you keep some sufficient amount of angular momentum so there is a rotationally supported disk. And I'll go through it briefly. There are three major mechanisms of non-ideal MHD. So first, there is the ambipolar diffusion, which is the relative motion between ions and neutral particles. So most of the time it's the positively charged ions at lower densities relevant to the disk and envelope densities. And there's also ohmic dissipation. Ohmic dissipation operates at higher densities. So if you have even higher resolutions to probe the secondary disk around a tiny protostar, you might need to consider the ohmic dissipation, but this is less important in our context. So both the two of them are diffusion mechanisms. So basically they reduce your magnetic pressure gradient and they also reduce your magnetic tension. And another effect is the Hall effect, which is this is very tricky. Actually, the Hall effect is direction dependent. It depends on, so basically it's the drift of charged particles when they travel in the magnetic field. So this drift direction depends on the sign of the charge. So if your medium is dominated by ions or by electrons, you actually have different Hall drift effect. And so this is the reason why some people perform simulations with the Hall effect and they see a bimodality in this formation. So we have an angular momentum vector and a magnetic field vector. When those two vectors are parallel, you see something like this. You form a disk, if I don't mistake. Yeah, when they are parallel, this is a parallel case. You form a very small disk, like a few AU, less than 10. And this is not a stable disk. It's rotationally supported, but the size will shrink in time, and eventually this disk will disappear because the Hall drift actually removes angular momentum from this disk and redistributes it outside in the envelope. And eventually, if you wait long enough, you will form a counter-rotating disk. So this brings you back to the anti-parallel configuration. Whether you start with parallel or anti-parallel configuration, always finish with anti-parallel configuration, where you have a stable, rotationally supported disk, and this is actually governed by the ambipolar diffusion. So eventually, we will have a disk size that is comparable to what you will get if you perform simulations with ambipolar diffusion only. And here are the scary equations. And we won't go into details. I just tell you there are three of the non-ideal terms. And those coefficients are the combinations of a lot of resistivity terms. And those resistivity terms depend on the charge and the number density of your charged particles and also the mass. And they also depend on the field strength. And also there is this characteristic collision time scale that depends on the density of your hydrogen. And so this can be very complicated to calculate if you don't have the right prescription between, the relation between field strength and density and also the chemical equilibrium. So that's why this kind of problem is very hard to study, and people performing simulations with all kinds of different chemical equilibrium, and they all get, somehow comparable results, but they all differ in details. And what we are proposing to do is to try to solve this analytically, but with a very simple approximation. So basically we take the angular momentum, the equation of motion in the rotation direction, and also the induction equation also in the rotation direction. We solve for stationary solutions. Basically, let me see. So basically, the angular momentum finds its balance at the place where the angular momentum brought in by accretion is cancelled out by the magnetic braking. And for the equilibrium of the phi component of the field strength, we have induction generated from the Z or R component, and there is the removal of the field strength through diffusion mechanisms. So we are going to mostly focus on this diffusion term. So if we balance those two equations, so basically we identify the two most important terms in those two equations, and we put the time derivative to 0, and this will give you a solution. And so it depends on where you are in this. The two most important terms could be different. And this is the rotationally supported disk that we usually see. Actually, you find the balance between the Faraday induction, vertical field transformed into horizontal azimuthal field. And this is the duration of the field strength, and this is the diffusion by magnetic pressure gradient. So basically, we diffuse the field lines upwards and downwards to decrease the strength of the azimuthal field. And this gives you a balance of roughly 20 AU, and depends on the mass to the power of 1/3, and also depends on the field strength that you have. And if we have Hall effect, then we will have an outer partition, and also we have a description for this, also this which is in the parallel configuration. So this is what has been studied. Well, this has been published a long time ago because it's simple. We have vertical field. But what happens if we have field lines oriented in other directions? Luckily, we also found a solution for them. So for this vertical field, this threaded with vertical field, we have this solution. And when it's threaded with a horizontal field, we can also have induction that generates the B5 component from the BR component, and the diffusion still happens in the vertical direction. And by balancing this, we can have a disk size which is larger. So here we get 50 AU and a different scaling mass of the star disk system. And if we combine those two, we can find this equation that gives you the disk size as a function of the inclination angle between the field lines and the angular momentum. So if we have I equal to 0, we recover the vertical case, and I equal to 90 degrees, we recover the horizontal case. And so here I show you the results. So to solve this function, you see the solution actually depends on the ratio between RH and RV. So we plot them here. There is a typical value of RH over RV, which is 2.8, and they have very weak dependence on the mass and the field strength. So basically, you can almost take this value for all kinds of environments, but still we solve for different values, and you can see for different inclinations. On the left-hand side, you find RV, and on the right-hand side, you find RH. And this horizontal field effect is only visible when you have really large inclinations. Otherwise, you are going to find values very close to a disk that has only vertical field components. And with this, we can integrate over the inclination angle distribution to get a disk size distribution. And that's what we did. So for different RH over RV values, I performed this integration for two distributions. So P of I proportional to psi I is basically a uniform distribution, and I also tested constant, which is a slightly more aligned distribution. And so there are the dark color lines and the light color lines here. So you don't see too much difference. So we really need pretty strong alignment in order to see a difference in the statistics. But so still we have three parameters here. And what I talked only about mass, but how the other two behave is more complicated. So these are diffusion non-ideal coefficients as calculated in two different works. and you already see different behaviors. And this depends on the grain size distribution and also the chemical model and the cosmic ionizing rays that we are using. So basically, if you use different chemistry, you get different disk size. You can have small or large disks. So what we did is actually we analytically calculated the dependence of the diffusion coefficient and also the field strength as function of the mass of your started system. So I have only 1 minute left. So this eta A, actually there are two regimes. So yeah, there are two regimes when this omega tau is large at low densities. So on the left upper left of this line, we have B over N of ion and N of hydrogen. And on the right, lower right side of this line, we have N over an ion. So you can solve this equation differently. And this ion density also follows different distribution in different regions. So we have a discontinuity here. Below this critical density and above this critical density, we have different behavior. So by assuming some profiles for U and also for rho, you can solve this equation throughout the whole domain, and you get B as function of rho, and we get the saturated value here. So basically for any central mass, you get a corresponding B naught, and then you can come back to calculate the eta. So we reduce everything to one single parameter, which is the mass, and then we solve the equation again. But here, so I try to compare with observation results by integrating over the IMF, but here you see this distribution is very narrow. It's all dominated by the low mass disk. So there might be some possible origin of discrepancies, but for those who are interested, please come and discuss with me. Thank you.
Okay, thank you very much. So next speaker, please. No, sorry. Or one question. I was told I have to be strict. Okay, Jizo. Then you break the rule yourself. Jizo, you break the rule yourself.
So I was just wondering, their observationally, their disk size and mass dependence has been measured, and whether you can use that to constrain your theory.
The dispersions are pretty large, so you can somehow they all, because the mass variation is not very large. Most of the protostars are pretty small. So and here we have a very shallow mass dependence. So you actually don't see you don't see huge variations in the size distribution. So it can somehow constrain, but there are too many parameters. So I wouldn't say it's a tight constraint.
Okay, thank you. Thank you, Benny. Next is speaker is the remote talk Yueh-Ning Lee.
I will share my screen anyway, whether or not you can me.
Where are we?
Can you see my screen?
Yeah, please share screen.
Okay.
So what was talk is
Okay,
on
so
Pebble formation or not in protoplanetary disk.
should I start?
Yes, please start.
Okay, hello everyone. So I'm Bobo. So I used to be the youngest PhD student of Pebble. The oldest one is Eric Ito. So Eric started working on something related to high mass star formation, and then switched to work on something related to radiation transfer. So do I. So I based on radiation transfer to look into the problem of whether or not Pebble forms in general in the plastic protoplanetary disk. And this problem is important because lately we know that for almost every single solar-like star, there's a rocky planet surrounding the star. So there's always a terrestrial planet orbiting the star. That's true for almost every of the solar-like stars. terrestrial planet, so we need to make the dust particle coagulate so all the way from submicron size, so which is the typical dust size in a cell medium, and go all the way to the 1,000 parameter size. And when your dust grain is having very small size, namely the micron size or submicron size, this is easy, so you can make the dust particles sticking with each other based on the van der Waals force. But when your dust particle is growing to bigger size, so say centimeter size, so we call them pebbles, so they look more or less like the stone, so you can pick up from the ground, so you can go to the ground floor. Then it's not trivial to make them stick with each other, so because the van der Waals force is actually very weak. So you can actually do the experiment today, right? So just grab two stones and try to put them together. And you'll find it is very surprising if they do stick with each other. So usually they don't. So classically, there's actually a size limit for whether or not the dust particles can stick with each other due to van der Waals force. And that size limit is about 100 microns. So classically, we call the size limit the fragmentation and bouncing barrier of dust coagulation. And so far, we still don't know how the dust growth can cross over the 100 micron fragmentation and bouncing barrier. And this is why we need some observation to give some clues about this problem. Observationally, we can anyway estimate the dust size, right? So we can see whether or not there's already some dust particle that the coagulation is already crossing over the 100 micron barrier. So to do this examination using observation, so what we do is we do the observation in image and sub in your band. So if you illustrate each dust particle as a small antenna, so you can illustrate that. So if your dust particle is bigger, then it can emit and absorb more efficiently at longer wavelengths band. So if you see the excess of long wavelength emission, you can infer that there's already some room in your Protoplanetary like this. Conversely, there's no emission in the long wavelength band, then you can say the dust spread may be saturated to the dust growth area of 100 microns. Then, so there has been a lot of SMA and AMA study to focus on this issue, and since there is a water snow line in the disk, so maybe Charlie introduced that, so typically less than 1 AU radius from the start. So the water snow line is very small, so all our observation will preferentially resolve the region outside of the water snow line, where the dust grain is coated with water ice. And all the previous observation, they kind of fit, they detect the long wavelength excess. So then everybody, so even in this review of PB7 series, they say the outside of the water snow line, so for whatever reason, the dust growth is very efficient and can easily cross over the classical bouncing and fragmentation barrier. Although we don't know exactly what is the physical mechanism to make it cross over the barrier. So when I looked into this problem, I discovered that there is an alternative interpretation for the long wavelength axis, which has been overlooked by everybody. So if you look at the assumption that scattering opacity, so if you look into the Jackson books, you'll know that the scattering opacity always follows the Newton's force law in the Rayleigh-Jeans limit. And the assumption of opacity always follows approximately Newton's square law. So that it means that they must cross each other at a certain frequency. And that frequency can be determined by the Rayleigh limit. So it's a wavelength that is 2 pi times the diameter of your dust particle. So if your dust particle is saturated to 100 micron radius, meaning that the diameter is 200 micron, then the Rayleigh limit is actually exactly 1 millimeter. So this 1 millimeter band observation, so if your dust particle is saturated to the fragmentation or bouncing barrier, then the observation of 1 millimeter band will happen to see the regime that the scattering opacity becoming more important than the absorption opacity, as increasingly more important at high frequency. So in that case, so the scattering will be more prominent at high frequency than the short wavelength band. So that is similar to our atmosphere, right? So you can make this analogy. So when you look at the sun during the sunset, more red line during the sunrise and sunset, it is peak. The more blue line is scattered by our atmosphere. And this can happen to our concentrated or 1 millimeter band observation when the maximum dust grain size happens to be saturated to the fragmentation and bouncing barrier on 100 micron size. So this is a hypothesis, and test it. And how do we test it? So by the analogy with the observation of sun during the sunrise and sunset, so the net effect of this sketch actually is to make your target that in terms of index, it means that it makes our spectrum anomalously low. So actually, when you're observing in the radiation limit, this is the only way to make the spectral index lower than observable matter. Radiation limit, and if you see the spectral index is lower than 2.0, then it means that the maximum dust particle size probably happens to be saturated to this gray limit of your observing wavelength. So then test this hypothesis based on the armor archival and for the nearest protoplanetary disk, the Hydra. Found that in the innermost region, so the inner fraction of second region, the spectral index is lower than 2.0, and the observation is still more or less in the radiation limit. So this result implies that the maximum in the innermost region of DW Hydra, so in this bright region, is only up to 100 micron size, which is smaller. And this is a correction of the estimate of dust size by 2 to 3 orders of magnitude as compared with the previous estimate. So then we conclude that so this specific target Hydra in the water snow line. In fact, the dust granules is not as efficient as what other people says. It's probably just accurate to the fragmentation and bouncing barrier. So this is just one specific case study. We try to extend this kind of case study to a survey of the class of disk in the Taurus and Auriga region. So this is a ICE-CSIC project of Zhong Jiayi, so she's probably there. So we use the SMA to measure the spectral index of 47 objects in the Taurus and Auriga region using 3 tuning. So we cover the frequency from 200 to 400 gigahertz. So she also provides a master thesis based on so she starts from proposing the observation and carrying out the observation, calculating the data, making all these measurements. So you can see very significant amount of work. Thank you. Thanks our colleagues at CFA, so especially Mark and Sean Andrew. So without their direct contribution, this work cannot be accomplished. So John is applying for a PhD position, so if you are interested in her work, so you're welcome to talk to her. So one of the major conclusions on resolve compact disk, you see the spectral index between 200 to 400 gigahertz very close to 2.0. For almost every of these protoplanetary disks, they show more or less in the same spectral index. And the actual implication for this spectral index distribution is that all the classes of disks we survey are in fact optically thick at this frequency band. So this implies a very big correction to the dust size and dust mass in this protoplanetary disk. Okay, so as Paul always asks us, so when you finish one work, he always asks, what is your next step? So what we did in the first 10 slides is the observation outside of the water snow line. And for me, the next step is to observe the region inside of the water snow line. And as you see, it's a very small region, so it's very difficult. But there are some sources that the distance heating is making the water snow line inflate by a factor of 10. So the radius of water snow line inflate by a factor of 10 due to some occasional outbursts. Outburst is driven by viscous heating, and the archival source of this kind. So still under outburst state. The region is water source. From little bit of trauma. Property inside protoplanetary disk. This is because the different wavelengths is tracing different depths, right? Different optical depth. So you can plot different region, the different scale high in the disk. And what we found is that in this disk, the midline is hotter than the surface because of the viscous heating. So then you can illustrate there's a 3D water snow line as a surface. And we found that inside of the water snow line, the maximum grain size, so we attend the lower limit, so it's bigger than 1.6 millimeters, so it's already crossed over the classical fragmentation and downstream barrier. In general, the water snow line, we only attend the upper limit of the maximum grain size, and it's less than 200 micron. So this is actually contrast to what other people believe. So people usually think the dust particle outside of the water snow line are stickier than the parasitic grain inside of the water snow line. And actually, from the observation of the viscously heated system, we can infer what is the turbulent strength, and then based on the turbulent strength, infer what is the collisional velocity between dust particles. Then we conclude that for this specific system, as you already so inside of the water snow line, the parasitic grain, the fragmentation velocity is in the order of 10 to 20 meters per second, so which is one order of magnitude bigger than the value for use for that's one dust here when no ice floated on the surface. And so there's a lot of debate about this result, so people kind of think I was crazy. Measurement that is consistent with measurement, so probably so in Tokyo Tech, who is working with Satoshi Okazumi-san. And also lately there is some update of experimental study. So there is basically use an experiment to test whether the water ice coated dust particle is more sticky or the parasitic grains are more sticky. And the experiment carried out after 2018 actually support that the water ice coated dust grains are less sticky. So it's more easy for dust to coagulate inside of the water. And so far, I seem to be concluding that planets tend to form in the region that is very close to the star, close star or close protostar. And this conclusion is very the water snow line, right? So it's mainly related to how the Earth formed. But then, so what happened to the formation of comets and the formation of icy giants, right? So they are still outside the water snow line. So I don't have a good answer to this question yet, but it seems like there can still form some grown dust, the pebble-sized dust outside of the water snow line, although we don't know exactly how. So here I'm showing the very high resolution ALMA observation for one of the classes. This ALMA band, the 1 millimeter wavelength band, this, although it presents some ring and perfectly azimuthally symmetric. But if we go to the JB of A band, we see there are some clumps on the inner edge of this azimuthally symmetric dust ring. And this clump is actually tracing some relation. So they have very restricted distribution, and they're located at some unresolved clumps. There's a whole lot of mass in those clumps, and the dust grain size in those clumps are bigger. And this is outside the water snow line. So somehow this grown dust particle may migrate to the inner edge, ring trapped there, and due to some perturbation, for example, by the gravitational force of the planet, become mutually asymmetric. Exactly, so detail to make this happen is something still uncertain. Okay, I'll stop my talk here, and thanks everybody.
Thank you, Bob, for being on top. Questions?
Hi, Bob, this is Dao Chong. It's good to know both of us are alive. How about dust polarization? What your comments are using dust polarization degree to constrain grain size?
Yeah, so using down polarization is basically using the same principle as the principle I'm showing here. So here, the anomalously reddening is the effect of dot scattering in stocks ion. And the linear polarization is the effect of dot scattering in stocks Q and U. Basically, they are tracing more or less the same thing. Observing stocks ion is like 100 times easier than observing stocks U and U. Basically, we get the consistent maximum grain size.
And any more question? One? Okay, no question. Next speaker. Thank you, Bobo.
Thank you.
Next speaker is Christian Flores, who's going to tell us about accretion streamers, protoplanetary disk, and outflow in the classified protostar Oph IRS63.
Right, thank you. So my name is Christian Flores, and I'm also here working with IOC. I'll be talking about one of the sources of EDs. So IOC earlier showed today about this great survey, this very large plasma program. And I'll be focusing on outflows, streamers, and also the disks. So this one. Here we go. So, this is almost like a mandatory picture to have for people working on EDs. And what you see here, as I mentioned earlier, this is the dust continuum emission for the sample of ED sources. In this particular arrangement, in the top part, what you see is basically the most embedded sources, so the youngest one, and the top in the bottom one is going to be the most evolved ones. So the class 1 sources kind of closer to the T-tally stack. But these are not T-tally stacks at all. Now, I think I usually mentioned already that the last two sources show some structures, some radial structures in the dust. And today we'll be talking about one of them in particular, which is Oph IRS63. For this source, we know that it has a reported annular rings and gaps. Actually, there was a paper published in Nature in 2020 by Tony Ciències. And this is very interesting because, of course, we need dust to create planets, but we must remember that most of the mass for creating stars and planets is still going to come from the gas. That's where most of the mass comes from. And I just want to remind you that although they all look like disks, these are not just T-tally disks. In fact, all these embedded protostars, as shown here in the simulation, are going to have an envelope that's going to be collapsing. It's going to have a disk and also outflows. And it's this connection, this dynamical interaction between all of these different agents that's going to, in the end, be important for planet formation and for the amount of material that we have to form planets and also to grow the star. So, in Oph IRS63, we detect an outflow. So I'm going pretty much here through the channel maps of the 12CO gas. Maybe what you can notice here is that it's a bipolar asymmetric outflow. And if I stop here these channel maps, you will see that there's a very wide outflow, and there's also an inner one, which is narrow. Now, if you even look in more detail, you will see that in the blue chip side, there are some narrow, like shell-like structures. So there's some like finer structures, which is very interesting because Seni told us on Wednesday that some of these shell-like structures is very small, fine structures can be produced, for example, when we have a jet or a wind interacting with the magnetized medium. So some sort of instabilities can happen and produce this type of structures. So when an outflow pretty much carves a hole in the environment, is going to interact here with the surrounding material of the protostar. In this case, it's going to be, for example, the envelope. And I think we're seeing an example of that here because the envelope, which is traced by a different gas tracer, which is C18, actually very nicely delineates just the edge of the outflow. So there's some kind of connection probably between these two different elements of the protostar. Now this envelope structure, as I mentioned earlier today, is going to be rotating but also infalling. And the shape that we have found for Oph IRS63 is kind of arc-like structure. So this type of envelope rotation and accretion is kind of deviating from this spherically symmetric collapse, and it seems to happen through this filamentary-like structure. And that's interesting because recently there's a lot of attention to these streamers, thanks probably to the high resolution that we're getting here with ALMA. So we have modeled these observations using this streamer model from Mendoza 2009. So it's basically saying that particles in the envelope are infalling into the disk and then in that way feeding the disk. And when we do that, we not only try to reproduce the spatial profile, we also want to reproduce what's the velocity profile. And basically we have particles starting very far from the cloud, that as they get closer, in the core, and as they get closer to the protostar, they're going to start like accelerating. That's kind of the signal we're looking for these streamers. There's another very nice observational result, which is this SO emission, and we see a very bright ring that you can see right there. And then there is some spiral structures that are just right kind of beyond that very nice ring. And what's interesting is that this rotation of these, or the apparent rotation of these spirals, is in the same direction that we see these streamers rotation. Now, they are not necessarily tracing the same gas because SO is known to be a shock gas tracer. And the scales we're tracing actually are very different. So again, on the left, that's the C18 integrated intensity map, and that's the scale of the SO emission. So very different scales, although they're proving pretty much the same direction. Maybe not the same kind of gas, maybe we're different. We're looking at different layers here. And also the pitch angle of these two spiral-like structures or arc-like structures are very different. For the SO, it's very tightly wound, while for the streamers, it's actually less tightly wound. So it was very hard to understand why we are seeing these kind of spiral structures in SO, but after talking to Ciències here and the Ciències also Nika, for example, and Ruben, we were able to, they told me about these very nice simulations showing that when there is a magnetized collapsing core that has a magnetic field that is misaligned with respect to the rotation, then one of the natural consequences is that they're going to produce these spiral-like structures. And in fact, in the paper by Wei-Xiaowan in 2022, what they were able to say is that because of the magnetic field, there's going to be some compression in the spiral itself, which might lead to shocks. Which is very interesting because, as I mentioned before, as I mentioned before, this SO tracer is thought to be tracing a shock gas. So that might be a possible explanation for these spirals seen in SO. Okay, so finally the disk. So these are 13CO C18 integrated intensity maps for the disk around this protostar. And I'm comparing that to the dust continuum emission, which is shown in red contours. You can see that they have an elongation in pretty much the same direction, so along the major axis, but they have different scales of sizes. So to measure exactly how much bigger is the gas compared to the dust, we did some kinematic analysis using a code developed here by Ciències and also Ciska called SNAP. We have been using that in EDISC a lot. And from that, we can recover that about the almost Keplerian rotation is recovered to about 250 or 60 years, which means that the gas extends about 4 times more than the dust, which may be some signatures of some radial drift for the dust. With this analysis, we can also give us the mass of the star. We can look at the pretty much almost Keplerian rotation and get a mass of about half a solar mass. And just from flux calculations, we can get what's the mass of the disk, which is about 100 Earth masses of dust, which is about, if we use a typical gas ratio, 30 Jupiter masses of gas, which is actually plenty of mass to produce, for example, the typical populations of exoplanets that we see around a half solar mass star. Now, I just want to reiterate that this is not a protoplanetary disk in the sense of an Itauri star. We must consider there's going to be more mass in the system than what we see just in the disk. And for that, we need to consider material that's going to be coming from the envelope into the disk, possibly through these streamers. And we have calculated what's the mass accretion rate of that. That's about 10 to the minus 6 solar masses per year, which is actually pretty high for this low mass star. Then we use infrared spectroscopy to calculate how much mass is going from the disk into the star, so how much mass the disk is losing in this way. We use infrared observations, and we estimate through microscopic accretion, it's about 10 to the minus 8 solar masses per year. And of course, some of the mass is going to be lost due to the outflow, and that happens. We don't really have an estimate, but typical values go to 10% or more of the mass accretion rate of the star. And as you can see, the first term really dominates for a few orders of magnitudes compared to the other ones, which then means that the natural consequence is that the disk itself is going to keep growing over time. It's already pretty massive. It's not on-Q unstable, but it's not too far. If it just continues accreting at this rate for another like 100,000 years, it might be unstable, and if it's unstable, it can develop instabilities. It might fragment and cause this variable accretion, like the one Doug Johnson was talking on Wednesday, and also can develop some other type of bursts, but that's just speculation, of course. So with that, I just wanted to leave you here with my summary slide, which is that for Oph IRS63, we have a very awesome outflow with many different substructures. We have detected these arc and spiral-like structures in CH0 and SO. We have these streamers. This is a conjunction between the envelope and the disk itself. That's maybe what we're going to keep finding more and more as we go to high resolution. In the EDISC, we have a few of these streamers, so you can go check the papers. And for the disk, we are detecting, in some cases, this almost Keplerian rotation for these protostars, kind of related to what Nayashi was mentioning today earlier. So please go and check the EDISC papers. These papers already published, and thank you so much.
Thank you, Christian. We do have 3 minutes for questions. Sona.
Thank you, Christian. Very nice talk. So, from the spatial location of the streamer, northeast streamer, it looks like it is just outside of the outflow. So, how did you distinguish between that? It is exactly a streamer, it is not the entering material from the envelope which is outgoing. How did you distinguish between the two facts?
Okay, so the analysis, so I think for outflow you do the PV analysis and you see this Hubble-like law, right? So you get faster as you go farther from the source For the streamer, you will see kind of the opposite. You start kind of very slow, and then you accelerate as you get closer to the protostar. Yeah. That's a way to disentangle the two of them, I guess.
Thank you.
Any other questions? Oh, Margaret.
Yeah, I was thinking of to your moment one map, the one you showed the velocity gradient.
Yeah.
So if you take a look to the right panel,
Yes.
you sort of see this kind of S structure.
Yes.
So Gemma shows something similar for the HIMARS regime. I think that Yoshi talked about that. We have seen this in some of the HIMARS sources. So is there any reason for this S shape?
Yeah, the S shape I think is showing basically info. So it's this change in direction between the disk and the envelope. And I think it's been known for some time. I think Shiga in particular, I think he's the one that pointed me that this S-shaped structure has been shown as a sign of info for quite some time. Yeah, under pressure, info under pressure. Yeah, so it's apparently known for quite some years now. Yeah, it was kind of new to me, but maybe not so new for other people.
Really?
Thank you, very beautiful results. So actually I have a different view on the accretion rates recently, because in simulations we kind of see that the mass accretion arrives at the star directly without going through the disk. So this might resolve your problem. So is there a way to actually observationally test where does the mass arrive onto the system? Because they can actually go directly into the star without going through the disk. And so what does not go into the star then goes into the disk?
I guess this really depends on how early you're talking about, right? This is a class 1 source getting much closer to the dowry phase in some way. Maybe what you're describing is like the very, second core collapse.
No, I'm talking about this phase. So
Oh, this phase, okay.
Yeah, but there's envelope and magnetic fields. Actually, the angular momentum can be lost during this info phase. So actually, the mass goes very close to the star instead of arriving on the outer edge of the disk.
So most of the observations doing through spectroscopy of class 1 sources show that the mass accretion rates are actually not that high. So most of the class 1 sources are going to be accreting similar to the dowry stars, maybe a little bit higher for the class 1 sources, not class 0. So it will be very hard to, think that the material going from the envelope is going to go straight to the star that way. I think most of the spectroscopy observations will not support that idea.
But at the same time, you have bursts in the accretion rates.
Yeah, exactly. So that's a good point. So maybe that's why we think that this happens through bursts, because the material is going to be accumulating this for some time, and then at some point we're going to have these eruptive variables like fjords and exors and how it starts getting most of their mass. For the most part, they actually accrete at a relatively low level, 10 to the minus 7 to 10 to the minus 9 solar masses per year.
Thank you.
Okay, let's thank Christian. So, the last talk of the morning is the Yueh-Ning Lee.
Okay, thank you. So I am not one of Paul's students. In fact, I think that for Paul, I probably appeared out of the blue in 2010 when I put in my application for a faculty position. But he ended up hiring me, and our collaboration therefore was more on a telescope project. So here in ASIAA, I have contributed to several projects, both on the infrared side and the submillimeter side. So I was part of NATIS, of Ciska, of JCMT, but above all I was part of ALMA, as I explained on Monday. And one of my main contributions in ALMA was actually the leadership of the Band 1 project. So shortly after I started, it became clear that the Band 1 project, there were several activities going on in the different ALMA regions, and this needed to be consolidated into a single receiver development project. So I was set out to coordinate the consortium, organize the kickoff meeting, and became the consortium's PI. And under my leadership, I led the project through the preliminary design review, the specifications review, the critical design review. We gained ALMA board approval for actually production, and we were preparing for the manufacturing readiness review. And now the result is there. ALMA Band 1, the Band 1 receiver, which operates from 35 to 51 gigahertz, is actually being installed on ALMA and has been offered to the community already in the previous proposal round. However, I'm here to actually talk about the science project that I did with Paul. And actually, we only have one science paper together, so I decided to talk about that because it's actually recently become very current. And it is about the unusual dimming of main sequence stars going from Kepler, which is the project that we worked on, to ASAS-SN, which is the more recent result. Okay, there we go. So the Kepler project started out in this paper from 2016 by Voigt et al., who looked at a particular star that was being surveyed by Kepler. Kepler was, of course, monitoring a field with lots of stars in it, and this particular one with the number 8462852 was an otherwise normal star that suddenly showed a series of very deep dimming events. The deepest peaks, you can see it on this plot here, actually go down to about 15 to 20% of the stellar flux being dimmed. It's also a sustained dimming event that lasted for quite some time, several months, I think. And the overall sort of the average dimming was at the level of a few percent. So if you treat this as a transiting object, then at any given time, at least 3% or 4%, whatever, of the star needs to be covered by something that's transiting, and at some moments this can be as much as 20%. So, the wrong direction. So, shortly thereafter, this team Wright et al. Actually came up with an explanation that invoked the presence of alien megastructures. I hear people laughing. This was a serious publication in the form of incomplete guys in space. And Paul came to me and said, "This is crazy. This doesn't happen. We should be able to actually come up with a more natural mechanism for this." So we decided to apply for DDT time on ALMA, SMA, and JCMT to constrain the dust present around this star. We were successful in getting JCMT time. ALMA was not successful, unfortunately, because the source was not really accessible from ALMA. And SMA time turned out that there was another team working on this as well, so we were asked to join forces. And this is what we came up with. So we put together this spectral energy distribution. And as you can see here, these are our measurements. So they constrain nicely the gold dust mass here. There is also a near-infrared data point here from WISE, which is consistent with the stellar photosphere. And there is a Spitzer upper limit here. So our measurements are also upper limits. So because of the near-infrared data point here from WISE, there was really a strong constraint on the warm dust component present, and we could not have dust warmer than about 160 Kelvin in the system. Spitzer put some constraint on an intermediate temperature component here, 80 Kelvin, And we have very, very generous upper limits here that allow for the presence of almost 8 Earth masses of cold dust. Of course, these are all upper limits, but it's quite difficult if you have this much dust. In principle, that's enough to obscure a stellar disk, but being this far out, where it's 30 Kelvin, it's actually really quite complicated to have it transit for such a long time because the orbital motion is so slow. So it was really a puzzle, and I think to this day it's still an open question what's going on here. In any case, a few years ago, in 2021, another object showed a very similar behavior, and this was actually observed by a supernova survey. And here is also an extreme dimming event here that occurred in June or so, or started in June of 2021. This was reported toward the end of 2021, and an ASIAA postdoc, John T. Marshall, who is in the audience here, actually started observing, following up this object with let me first tell you a little bit about the SES in 21QJ. The star is actually strikingly sun-like, as you can see here. So it's at a distance of 550 parsec, and all these parameters are very much sun-like, and it is a solidly main sequence star. There's a large error bar on this age. It's 6 plus or minus 3 gigayear, and this is because it is on the main sequence, there's not much happening to this star, so it's very difficult to actually determine the age, but it's solidly main sequence. And so we put together this additional, this light curve with additional data, so John T. Marshall took the lead on that and used the Las Condes Observatory Global Telescope and other facilities to put together a light curve, and meanwhile ASAS-SN also continued to observe this source. So these data are all combined in this plot that we published earlier this year, and we established that there was a period of about 30.9 days, and we tried to find further peaks in the extinction and time our observations accordingly. We also, in this paper that we published in August, we were also able to say something about the grain properties of the material that extincted the star by looking at color diagrams. So we basically put together at different epochs, we took measurements of the color values and put together this extinction law, or these two extinction laws, and found that they're consistent with small amorphous silicate grains, sub-micron sized silicate grains, throughout the event of the dimming. In addition to the dimming, we found that there was a near-infrared excess, as you can see here in the lower two plots. And as you can see, the near-infrared excess, it's hard to tell when it really started, but it's well before the dimming event, which is here. Yeah? So it started about 2.5 years before the dimming event, and the color of this near-infrared excess points to a dust. So if you assume dust with the same physical properties as what we just derived the extinction, the near-infrared brightening is due to a dust component somewhere of the order of 700 to 1300 Kelvin. And the near-infrared excess is sustained throughout the dimming event, but kind of ends at the end of the dimming event. So we find that the period and the temperature of the orbiting dust cloud are consistent with each other and point to a orbital radius of 0.2 AU. So this is about half the radius of Mercury, the orbit of Mercury. We therefore assume that the dimming and the near-infrared brightening is actually caused by the same dust. And so the event here happens that causes a dust cloud to form, which becomes visible in the near-infrared, and then after 2.5 years, which corresponds to roughly 30 orbits, part of this dust, or all of this dust, somehow appears in the sideline. So maybe some kind of precession going on, or the dust cloud expands. It takes some time before it actually starts transiting the stellar disk. We are able to calculate the dust masses involved and find that the total dust mass, as it is determined, as you can determine it from the near-infrared brightening, is 2 times 10 to the minus 6 Earth masses. And the transiting dust cloud at any given time is about 1.5 times 10 to the minus 9 Earth masses. So that's for the deepest dips in the light curve. For comparison, I've shown some masses of solar system objects. A comet like Halley or Hale-Bopp is about 10 to the minus 10 Earth masses. Ceres, the largest asteroid, is 1.5 times 10 to the minus 4 Earth masses. And Mercury, the smallest planet in our solar system, and sort of equivalent to a potential planet around this star, is 0.055 Earth masses. So we stipulate that the masses contained in smaller bodies in the solar system are actually more than sufficient to produce the dust that we need. So a collision between 2 such bodies is probably the source of this dust. And we talk about volcanoids here because it's kind of inspired by the planet Vulcan, which was hypothesized to exist in the solar system inside the orbit of Mercury. And a corresponding population of asteroids would have the name volcanoids. So you could have a collision between 2 such objects that would produce the dust cloud required. You could also have a star-grazing comet like this one that disintegrates when it moves close to the star, although you see here that the remnants continue on the same parabolic orbit actually, so maybe that would work so well. Or you could have the impact of a high-velocity comet onto a Mercury-like planet, or rather a Vulcan-like planet. This was all put forward at the end of August 2023 in APJ. A few weeks ago, an alternative scenario was put forward in a Nature paper with a tremendous news coverage. In this scenario, they analyzed the same data, they also found the same near-infrared access in the NEO-WISE data. But their hypothesis was that the 2.5-year delay between the near-infrared brightening and the optical dimming event happened within 1 orbit. In other words, the dimming event happened when the dust cloud transited or moved in between the star and ourselves for the first time. This makes the orbit at least 2 AU in radii, because it has to be at least 2.5 years in period. So this is the scenario. And that means that the dust cloud is actually difficult to keep warm. And in order to actually come up with an explanation for the near-infrared emission, they invoke the collision between 2 ice giants, like this. And modeled this collision indeed. Here you see that this collision takes place over 70 hours, so a couple of days time sequence. And you start with 2 ice giants in the beginning and end up with a small post-impact body that is warm. It retains the impact heat, so that is the near-infrared source, and a large cloud of debris, which is cold because we're far from the star now, and actually is very much dispersed, which produces the dimming. So that's their scenario. Of course, collisions between ice giants are very unlikely. By the definition, the physically motivated definition of a planet, planet orbits are empty of other planets. They're just alone in their orbits, so it's not likely that you'll have a collision, certainly not in a mature planetary system. So they went around this by saying that the star is actually very young, and this was based on some variation that was seen in the light curve on a very small scale with a period of 4 days that was due to star spot activity. Now, of course, that team and also us are both planning follow-up observations to distinguish between these scenarios. And the follow-up observations are going to be focused on two different aspects. First, we need to determine the stellar age, and the other point is that we need to look for thermal emission from this dust cloud to figure out what the temperature is, and we look for signs of small dust grains, spectral features of small dust grains, to establish that indeed we're looking at a debris cloud. Now, there's another aspect that we can think about, and this is maybe in the line surveys. If this is an impact between large bodies, this is sort of an extinction level impact that happens also in the solar system. We know that this happens. And here this diagram shows basically the probability or the frequency of impacts as a function of size of the impacting body. So if you look at 10 kilometer size here, which is the sort of size that you need to cause the extinction of dinosaurs, that happens once every 100 million years. So in other words, if you give it enough stars, you can actually look for these sort of things in large surveys. And I'm thinking of, for instance, Rubin. So my conclusions are that both the Kepler object that we looked at with Paul and ASAS-SN21QJ are both extreme dimming events, but unlike the Kepler object, in ASAS-SN21QJ we actually see a bright near-infrared component, which implies the presence of warm dust or perhaps a thermally emitting object. We explain this by the catastrophic breakup of a small body inside the orbit of Mercury, or what would be the orbit of Mercury, but other scenarios exist involving colliding ice giants, and future observations will distinguish between these scenarios. We think that these sort of, according to our scenario, these sort of collisions are very common, relatively common, and we can look for them in, for instance, Rubin, Gaia, or neolized data, and we're currently working on this already. And if we find more of these events, this will help us to gain further understanding of the evolution of planetary systems, including our own solar system. Thank you.
Thank you. We go to lunch. So if there's no question, let's break for lunch. So we have, Paul.
So theoretically, one must be able to make an estimate, right? How likely are ice giants to collide versus comets colliding with the planet, right? Because comets, we have a cloud, you can calculate statistically.
Yeah.
Ice giants, typically in the system, there's not that many, so the collision likelihood must be much lower. Is there anything on that?
Not yet. So this is also part of our future work. So we want to look into this in more detail to see if we can estimate probabilities of these things happening. But yeah, if you look at it, just by just the very fact that we have these extinction level events every 100 million years or so, you know that these things happen in the solar system. So the probability is high. Ice giants colliding, I don't think we have any record of that having happened in the solar system. Right? So yes, that's our data point already there. But yes, we need to do a bit better than that.
Okay, really no more questions? Let's break for lunch. But Kang has something to say.
We will start at 1:45.
Oh.
Yes. Okay. So lunch is ready. So enjoy it.